Good morning, everybody. Today we have a global round, Codeforces Global Round 19. Now, the last time we had a global round, as you may or may not remember, I lost 199 rating points, which is the worst contest of all time. This time, hopefully it's a little different. So let's jump into it. Should have prepped this ahead of time, huh? All right, here we go. Here comes the contest. We'll start with problem A as usual and get rid of some of this stuff. Come on, computer, you do it. All right, we have an array A of length n. You can exactly once select an integer len between 1 and n minus 1 inclusive and sort the prefix of the array len and the suffix of the array n minus len minus 1 independently. We can sort the prefix and then sort the suffix. Could it be possible that after performing this operation, the array is not sorted? Well, we'd always choose n minus 1, right? So is the last number 1 or is the first number the biggest? Yeah, if the first and last number are in the right place, then it doesn't change. Okay. Oh wait, so if the first number can change, but if the first number is the biggest, ooh, interesting. So if the last number is equal to the min and not equal to the max, then it's impossible. Or if the first number is equal to the max and not equal to the min. All right. So first equals max and first is not equal to min, then it is possible, so yes, else, wait, what'd they say? Wait, so is the question just, is the array sorted? Oh, and the suffix. Okay. N minus length. So you're splitting it in half and sorting the two parts. So the question is just, is there any decrease? Right? Because or is there any decrease? Yeah, if there's a decrease, then if you have a decrease, and you pick this, the decrease won't get fixed. Yeah. Okay. Int array clone equals a.clone. That's a good problem. If or matches and equals clone at I equals a at I. If it does match, print no, otherwise print yes. Whoa, that was slow. My goodness. All right. Next array. Let there be an array B. Let a partition of this array into segments. Let there be a partition of the array into segments L1 to R1, L2 to R2, etc. Okay, so we're partitioning the array basically. I see. Let's define the cost of a partition as C. What is C? Oh, C is the number of these things. C is the number of groups. Yeah, I guess C is the number of groups. The cost of one partition is C. Oh, okay. So the number of groups plus the sum of the max of what is B. What are all these B's? So for each range, we take the max, and then we add up all of those maxes and then add C. Okay. Or max, yep, we know that. Okay, in other words, okay, this is what I should read. The cost partition is the number of segments plus the max over all segments. Sum of the max over all segments. Let's define the value of the array, B1 to Bk, as the maximal possible cost over all partitions of this array. The maximal possible cost. Okay. Over all partitions. Find the sum of values of its subsegments. What is a subsegment? Does this ever matter? If you include one more element, wait, what is a subsegment? Oh, from the beginning and the end, so a continuous part, okay. All right, so why not just split at every position? Yeah, if we have a 0, whatever, and then if we have a 1, we either get +1 for this being a new range, or we could get +1 for including in the 0, but why do that? So this 4 is just, does an empty subsegment count? So we have empty, we have 2 things of size 1, 1 thing of size 2. So that's where the 4 comes from. For this, we have empty, we have 3 of size 1, we have 2 of size 2, we have 1 of size 3, and then the 0 is part of 1, 2, 3, 4 of those, so +4. That gives us a total of 4 plus 3 plus 4, which is not 14. Let's think about it. Okay. All right, 2, 0, 1. So we have 2, 0, 1. So this is 3. And then we have the empty, which is 1. Then we have 2, 0, 0, 1. This gives us 2. Then we have 2, 0, 1. This gives us 1. But then we have 1, 2, 3, 4. So this is 4 plus 3 plus 4. That's not right. The second case, okay. The best partition for the subsegment 2, 0, 1 is 2 and then 0, 1. The cost is equal to this. Max of is equal to 4. Oh, because we get 3 for this. So this gives us 2 times 2, and this gives us 1 times 3. Okay, so we have, so this gives us 4 plus 8, 11. What's 11 plus 4? No. Each of these are length 2, so we split them up equally. These are length 3. So yeah, we split them all up. And we get a 4 here, 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 and here. Why 15? So everything gives you 4. Am I counting that right? So yeah, everything gives you 4. For 2, 0 gives you 3. Yeah. So one of these and one of these. Okay. So why is this 4, I guess? I guess I'm counting the empty one. So why is the 1, 2, 1, 2, oh, 1, 2, yeah, okay. All right, okay, so it's easy. So the question is, we want, yeah, we do this pretty easily. Oh, n's really small. Nice, nice. Yep, okay. So ans plus equals r minus l plus 1. And then we can do n cubed on this for in k equals l, k is less than or equal to r, k plus plus, if a at I, or if a at k equals 0, ans plus plus. All right, Andrew has n piles with stones. The ith pile contains ai stones. He wants to make his table clean, so he decided to put every stone either in the first or nth pile. Okay. Andrew can perform the following operations any number of times. Choose 3 indices such that the jth pile contains at least 2 stones. And then he takes 2 stones from pile j. Choose 3 indices. The middle one contains at least 2. Then take 2 from j, put 1 in I and 1 in k. All right. What is the minimum number of operations he needs to move all stones to piles 1 or n, or determine that it is impossible? Okay. So let's think about it. It's probably usually possible, I would imagine. we can do something like this. So if we have, if we have a 2, and then, so piles 1 and k don't matter. They're like garbage cans. If we have a 2 in here, we can have any number of 1s. And obviously anything bigger than a 2. Anything bigger than 2 we can subtract 2 from in a turn. For any 1s, we can fix a 1 in a turn. So we can -1 and then +1 here, or -2 +1 there to fix a 1. Yeah, so like a 1 costs us +1 turn to fix. Every 2 costs us +1 turn, or like mod 2 over 2 turns to handle. And I think that's it. Okay, and then we need greater than or equal to 1 thing that's at least 2. So let's look through a sample. So we have 1, 2, 2, 3, 6. So these don't matter. What if this is a 3? It has to get fixed too. So 1 thing has to get fixed, and then we have 3 turns, 1, 2, 3 for removing things. That gives us 4 turns. Okay. Yeah. How does this work? So delete this, yeah, pretty easy. Okay, this is, oh, that's another case. So we need, we can't have not just 1 odd either. Oh, we can sometimes have an odd. You can have a 5, right? Because the 5 can go 1, 3, and then the 5 can go 2, 1, 0. Yeah, okay. So not just 1, 3 odd in the middle. Okay. Yes. All right, so we need the array. So int n non-zero, max n ones, n odds. Okay, so if max, all right, so if n ones equals n non-zero, oh, I guess, okay, so if n non-zero equals 0, then sys out 0. Oh, this is not true. Okay, so print 0 and then continue. If they're all 1s, sys out -1 and then continue. What else? There's the 1-3 case. So if n1s equals n non-zero, minus 1 and max equals 3. So this out minus 1 and then continue. How many turns does 5 take? So 1. Oh yeah, 5 might be a bit slower. So 5 we say is possible in 3 turns, but I don't think it is. You have 5. Oh. What if you just have 1? So just 1 3 is possible, but a 5 is not possible if there's not enough room. Okay. If n non-zero equals 1 and n equals 3 and max mod 2 is equal to 1, sys out -1. So just a 5 with no room to fix. Okay, otherwise we will have, well, yeah, so otherwise, yeah, what is the just 5 case? The just a 5. So if we have a 5 on its own, we have to do 1, 1, 3, and then 2, 2, 1, and then 1, 2, 2, and then 2, 0, or 3, no, 2, 0, 3. So this is 1, 2, 3, 4 turns. Yeah. So if n non-zero equals 1 and max is greater than, or and max mod 2 equals 1, sys out max over 2 plus 2. Continue. Otherwise, sys out max, or sys out, oh, this is total. Okay, so this is n odds plus n odds plus I over 2, or plus pairs over 2. I think that's it. Not it. First one I'm saying 3. 1, 2, 3 plus 1. Number of odds has got to be 1. Number of pairs has got to be 1, 2, 3. Oh. Three pairs, how are there 2 odds? Looks right. I guess let's do some additional testing here because this is sketchy. Okay, so 2, 5, 5. Oh. Say okay, so we've got 10 test cases, 2, 5, 5, 5, 5. All right, and then say we have 3. So 1, 4, 1. 2 turns, yep. Let's say we have 3 and it's 1, 5, 1. That's going to be impossible. Okay. 3. Or let's say you have 4. 1, 5, 1. And then a 1. So 1 turn for that. 1 turn wasted. So it's the same as. Wait, is this right though? 1, 5, 1, 0. So we have 1, 3, 2, 0, and then then we have to go back and fix this. Yeah, so 1 went here, 1 went there. I think that's right. Yeah, so then 1, 4, 0, 1, plus 2 more. So 1, 2, 3, 4. That's right. Okay. Yeah, I think we're fine. See, wrong. All right. So why you test? So if there are no non-zero, the answer is 0. If there are no non-zero, the answer is 0. If everything in the middle is a 0, then take 0 turns. If everything in the middle is 1, it's impossible. Yeah. The number of 1s, if we have 1, 3. That's not true. How did I get this case? Oh. I don't think that's true though, because you got 1, 3, 1, and then you have 2, 2, 1. Yeah, that's what I'm looking for. Okay. Just a 5 with no room to, yeah, so I think this is the solution. Test 1? Oh no. This is why you test pre-tests. Really? Number of 1s equals 0. Max equals 3. Oh. And yeah, here you go. N non-zero. And the number of non-zero equals 1. We can rerun this, but I know I'd get it, and I know that I'd resubmit as soon as I got it, so there's not really much sense in waiting. Okay, got it. All right, on to D. Nope, I wanted that problem. Okay. Here we go, here we go, here we go. We have 2 arrays. This is an exciting contest, I gotta admit. We have 2 arrays. Global rounds, always fun. Sometimes they're a little depressing, but it's always a fun thing to partake in. We have 2 arrays, A and B, both of length n. You can perform the following operation any number of times, possibly 0, where we select an index, I, and swap AI and BI. All right. Let's define the cost of an array A as the sum of all pairs of distinct elements. Similarly, the cost of array B, oh, distinct elements squared, I see. Similarly, the cost of, yeah, we got C a while ago. Thank you, 0, for catching up. Similarly, the cost of array B is the sum of all elements squared. We want to minimize the total cost of the 2 arrays. Each test case contains several cases. N is tiny. Woohoo, okay. Okay. So what does this cost function look like? A plus B squared equals A squared plus B squared plus 2AB. So we can more or less ignore this because it's going to be there for everything no matter what. So the question is this 2AB thing. So everything's multiplied by 2, so that doesn't really matter. So we really just have A times B. So we want to minimize the pairwise products. In both arrays. C, and the elements are all small. So we can have dp at top sum equals min cost. Yeah, that works. So how many choices do we have here? We have 10 to the 4. So n squared dp. Yeah. Oh, it's a multi-test case? Oh no. Sum of n over... I think this is fine then. Okay. Alright, so dp, yeah. Okay. Oh, we need the top sum and the position. So this is harder than I thought. Okay. Back to the drawing board for a moment here. Top sum. Okay. And then we also have the position. Top sum and position. And there are 100 of these. So it's still almost certainly a dp equals the min cost. Instead, do we want dp at difference? So like top minus bottom. So if we had some old top minus bottom, the new top minus bottom will be this like plus the new difference or minus the new difference. Yeah. I think that's fine. So this is int difference. Okay. So if position equals 0, then we will return 0. What else? So then oh, sorry. All right, so this is for returns min pairwise products. Yep. All right. So then long min base ants equals go of 0 and n minus 1. And then long real ants equals 0 for n equals 0 less than n I plus plus. Real ants plus equals 8i times I guess just 8i. plus b at I times b at I. And real ants plus equals 2 times min base ants. This out. All right, easy part's done. Now for the hard part. Oh, I guess we have to do this dp. All right, so then dp equals new new int array. This will be static int offset will be I think this should be fine. This is 2 times 10 to the 7 is our final runtime. Okay. For int I equals 0, I is less than dp.length plus arrays.fill dp I with -1. Oh, yeah, that's fine. So if dp at top minus bottom plus offset position it's not equal to -1, return this thing. And then otherwise we have int min ants equals integer dot max value over 2, and then return this equals min ants. I think we only have 2 choices here. Yeah, only 2 choices. So one sec, be right back. So this doesn't actually start at 0. Okay, so then, yeah, we need to brute force what this offset is. Min base ants equals math.min, min base ants, or go offset to use which position? Position n minus 1. Okay. Guess this needs to be a long, huh? Yeah, it's gotta be long. And then this needs to be long dot max value over 3, long dot max value. Oh wait, are all of these things small? No, they can all be ints. Okay, never mind. Yeah. Yeah, it's 10 to the 6 max. Okay. So skip that. Otherwise, we probably need prefix sums, right? Yeah. Static int array prefix sums. Prefix sums equals new int array n plus 1. Prefix sums at I equals prefix sums at I minus 1 plus A at I minus 1 plus B at I minus 1. All right, so this is the top and the bottom for everything before us. Okay, so equals 0. This is easier. Okay, so then this needs to be when we start. Where's this offset? Minus offset. What's the offset? Okay. All right, so this is just a number, top minus bottom, and so on. Okay, so some stuff happens. I guess maybe we should be careful with this, but okay. All right, so yeah, this is the base case. Base cases are over. Okay, so now let's actually solve this. So int, or I guess int cumulative total, I guess, will be can keep the same order, or we can switch the order. So int top will be A at position, bottom equals B at position. Int next top sum will be I guess we need the current top sum. So int current sum equals prefix sums at position. Int current top sum equals current sum times 2 minus top minus bottom. Oh, how do you do this? Okay. Plus top minus bottom. So let's say you've got like 3 and 2. So then the sum is 5, and top minus bottom equals 1. So 5 over 2 is 2.5. Okay, I think you want current sum plus top minus bottom over 2. Okay, and current bottom sum will be current sum minus current top sum. So next top sum will be current top sum minus top. And next bottom sum will be current bottom sum minus bottom. So we only want to do this so if current top sum is not equal to, or current top sum minus current bottom sum is not equal to top minus bottom, and throw null. Okay, so we have the next top, next bottom sum. Yeah, so then so the cost will be go of next top sum minus next bottom sum, position minus 1, and then cost plus top times next top sum plus bottom times next bottom sum. And then min ants equals math dot min of min ants or cost. Okay. I think we're done. Time to debug. Well, what's this first one? $45, huh? Why 45? Oh, this is okay. This thing times, where's the times button? Yeah, each of these things are this many other pairs. So that works anyway. So now we crash. Okay, so why is this? if top minus bottom mod 2. Okay, so Boolean should be even equals top minus bottom mod 2 equals 0. Boolean is even equals prefix sums at position mod 2 equals 0. If should be even is not equal to is even, then return integer.max value over 3. Definitely not right. Okay, so this is the problem, which is max value over 3. Yep, so why? Um, 3, 2, 1, 1, I guess. Okay. Yeah. All right, so what is dp at top minus bottom? We can do at 1, position equals 0. Top minus bottom is 1, position is 0. What the heck? position plus 1. $987. Okay. Oh my goodness, it took me so long. Ah. I'm so slow, so slow. Anyway, it took me like, oh my goodness. So slow. All right, let's get E. Please. All right, we have an array A of length n. Let count of x be the number of elements in the array which are equal to x. Also define f of xy equals count of x plus count of y times x plus y. All right, we're given m bad pairs x, y. Note that if x, y is a bad pair, then y, x is also bad. Makes sense. We want to find the maximum value of f of u, v over all pairs such that u is not equal to v. Wait, when is a pair bad? Okay, they don't tell us, or they just give us some pairs that are bad. All right, we want to find the maximum value of f u, v over all pairs. So we're going to pick two numbers. We want the maximum value of this function such that u is not equal to v. Oh, that part doesn't really matter. Okay. That this pair is not bad, and also u and v each occurred in the array. It's guaranteed. Stop guaranteeing things. Why not just say it's like we promise such a pair exists, or I guess such a pair will always exist by input constraints. I don't like this. I guess it's not terrible. It's pretty obvious what it means in this case, but okay, so ignoring the pairs that are bad, we want to find the maximum value. Is that the case? Yes, right? So other than these ones, find the biggest one. Find the biggest one not in the set of bad pairs. Got it. All right. Square roots seem important here. This doesn't seem that hard. So let's say we brute force, let's say we know count 1 and count 2. So we know we just want to find the best x plus y, where like x is in A, y is in B, and then like xy isn't bad. And we want to do this in order like number of bad amortized. So this is what we're trying to solve, because there are only like order n of these, because you can only have square root different types of counts. So this is observation 1, which is maybe not that hard to make, but so we have like some numbers here. We've got like 1, 3, 6, 9, and we've got like 8, 2, 8, 2, 1 maybe. Oh, there will be no overlap. There will be no overlap. Okay, so we'll never have this because of the constraints of the problem. Then we've got some bad edges here. So yeah, like this one, maybe this one, this one, this one. And we know can we say for each one of these it will only be in one thing? I think so. There are a lot of reasons this could be fast. Yeah, it probably is fast. Probably just don't quite have the proof for it, but it's probably fast. There are also a lot of ways we can break early. So, all right, we've got, how does this work? We have like a number, like some value goes into the count of that value. Bucket. I guess we might as well coordinate compress first. Yeah, probably coordinate compress. Then each value has a count of value, okay. And then we'll do n squared on the buckets, which is fine. Yeah. And now we need to like find best pair on all buckets. Probably breaking up pretty quick. Okay. We'll get this problem for sure. Then hash map integer. So this is compress. Map.put or compress.put. Compress.size. Okay, so value of ID at compress.get a of I equals a of I. Sounds good. Okay, so we compress everything. All right, so now we need some buckets. Array list of integer non-null buckets. Just new array list. How many are going to be in this? N plus 1? Is less than n, I plus plus. Well, I guess for an I and a, count of ID at I plus plus. Okay. So now we have the counts of everything. Okay, so then for I equals 0, I is less than a.length, I plus plus. If count of ID is not equal to 0, then if buckets at count of ID equals, okay, wait, what is this? If buckets at this count equals null, then buckets at count of ID equals new array list, and then non-null buckets dot add buckets at count of ID at I. All right, so yeah, okay, now we need buckets at count of ID at I dot add this thing. Oh wait, dot add, yeah, dot add this ID. Okay, now we have everything in buckets. What the heck? J equals I plus 1, or J equals, the counts can be the same, right? Yes, yeah, J equals I. J is less than non-null buckets dot size, J plus plus. Now we need to check this. So what do these bad pairs look like? We have n and number of bad pairs. Okay, oops. Okay, so yeah, so now we have 4 int, oh, yeah, I equals 0, I is less than n bad pairs, I plus plus. And first equals this, second equals this. Bad pairs dot add to long, first, second, and then add second, first. And then we can just do this, and it makes it so easy. 4 into I and A. We'll say bad pairs dot add I or to long, I. Look at that. Nice. Okay. Very clean, very clean. So now we just need to do this. Static void, or static, what is this? what do we print? The answer to the problem. That's unhelpful. Output maximum value of f of n. Okay, so static long get max. We're gonna need a whole bunch of stuff, but that's fine. So array list integer ID is 1, array list integer ID is 2. Then we're gonna need the counts of ID. I think that's it. Oh, we need the list of bad pairs, but we've got that already. Static boolean is bads into A into B. Return bad pairs dot contains to long in B. Okay. Best equals math.max of best or get max non-null buckets dot get I, non-null buckets dot get j, or what's the last thing? Counts of ID. Okay, so that's all fine. So now, how do we do this part? I guess we can do this thing. So static long int val int A int B int array counts of ID. So return counts of ID at A plus counts of ID at B times value of ID at A plus value of ID at B. Okay. If the first one size is less than the second one size, we'll take the first one. Otherwise, ID is 2. Okay. So then for I n smaller. What's the wrong answer rate on this, by the way? 300. And how many submits? Ooh, I'm doing terribly. Okay, so most people are getting it right. Or at least passing pretests. So then int best big equals -1. so okay, so if eval of smaller index bigger, well, if smaller dot get smaller index bigger dot get match with if this is less than or equal to best, then continue, or then break, I guess, because it's only going to get worse. Okay. If not is bad. Okay, so I guess int val small val equals this. Big val equals this. Okay, so yeah. If not is bad, then is bad. Okay, then break. Best equals math.max of best and eval, small val, big val, counts of ID. Best big equals match with. If best, or if match with equals bigger dot size -1, then break outer. So each time we do this inner loop, I think this is actually quite fast. $48. Oh wait, this bad pairs might be wrong. Yeah, the bad pairs is wrong. Okay, so we need, this is value of ID. And then this is, oh, I guess we could just compress it. Before we compress it, it's fine. Do we TLE? Hang on, go back. Print writer. Let's just use it just in case. Wrong answer. Oh no. I'm a fool. That was a dumb submit. That was dumb. I'm dumb. I'm so dumb. Oh, I have a negative IQ. The only thing lower than my IQ will be my rating after this round. TLE, test 5. No, good. Not complaining. Okay, not horrendous. Let's get F and call it a day. What do you say? How are my friends doing? We'll see. Let's get F. Yeah, they're... Holy cow, dude. Holy cow! People are crushing it. Go get it. Okay. Towers. 56 minutes. Come on, we can do it. We can do it. Problem F. Okay. You're given a tree with n vertices numbered 1 to n. The height of the ith vertex is hi. We can place any number. Ugh, I'm old. My back is cracking. You can place any number of towers onto vertices. Wait, what? What about towers? Okay, we're introducing towers now. You can place any number of towers onto or into vertices. For each tower, you can choose which vertex to put it in, as well as its efficiency. Setting up a tower with efficiency E costs E coins. Okay. So you get some efficiency, and you're going to put some towers. You can place any number of towers into vertices. Okay, so we have some we've got a tree. We're going to put some, we have a tree with heights, okay? And we're going to put some towers on each vertex, where each of these towers has an efficiency with a certain cost. Okay. It's considered that a vertex X gets signal if for some pair of towers at the vertices U and V with efficiencies EU and EV, it is satisfied that the minimum of these two is greater than the height of X. And X lies on the path between U and V. All right, you get signal if there are some people that cover you that are both taller than your tower. Is that what I'm understanding correctly? Yeah, okay. So, I see. So all of the leaves need to be at least themselves. Yeah, let's do an example. This is a complicated enough problem. I don't want to misread it and then spend my last hour solving something that doesn't exist. All right, so we have a tree. We have 1, 2, 3. Here's the edge. Here's the edge. Okay, what are the heights? The heights are h equals 1, h equals 2, h equals 1. Okay, observation 1, we only ever use heights that are given to us initially. So we'll coordinate compress, probably, I don't know. Maybe, well, we can maybe coordinate compress. Okay, so one thing is just 4, but you can do 4 in a different way. You can do 2. The min of these two is at least h. So the answer is 4, okay. If this were a 1, what if these were like, okay, this is kind of boring, but what if they were like 2, 2, and 3? 3 and 3? Yeah, then you can do 6, which is better than 7. So you can essentially move this to any one of your kids, and then, or to 2 of your kids. Yeah, you can move your value to 2 of your kids. Maybe? Is there any reason not to always do that? Yeah, there might be. Wait, no, there's not. Yeah, because it's got to be 2 things, and u isn't equal to v. Wait, some pair of towers, u and v. So where they're different. So you have to move your value to 2 kids. So you're always just going to pick leaves. There's no reason not to pick a leaf. Yeah, there's no reason not to pick. Oh, or is there? I don't think there's a reason not to pick a leaf. You always want to pick a leaf. Yeah, so we're just going to pick some leaves. Okay, let's do sample 2. So we have 1, 3, 3 to 4, 4 to 5, 3 to 2. Okay, it's a pretty normal looking tree. And then the heights are 1, 3, 3, 1, 3. So you pick 3, 3, 1, and 1. That's your answer. 6, 7, 8. 7. We don't, this isn't a leaf. Yeah, okay. Well, these aren't helpful samples at all. This is not helpful. Not helpful at all. Not helpful. All right, so let's make a good sample then. So we've got some more complicated tree. So initially, all of the leaves have their own value. So we'll make all of the leaves, I don't know, like 1, 1, 2, 3, 1, 1, 2 or something. Okay, so all the leaves have their own value. Okay, so we need another leaf to be 3. Oh, is this centroid decomp? Centroid decomp, centroid decomp, centroid decomp. Or we could go from biggest height to smallest height too. Oh no, 47 minutes. Time is ticking. Probably only needed like 30 to implement this, so we got like a good 17 to figure it out. Okay. So let's say we go from big to small. Let's say like this is the, maybe this is like the biggest thing. This is like a 12. So we have to give two kids a 12. Yeah, we have to give two of these three kids a 12 at least. Which two do we choose? I imagine this probably has lots of wrong submits, huh? There are lots of ways to get this wrong. Not as many as I would have guessed. Well, I guess we can be greedy, right? If we want. So we make the two biggest things here. So like fill this in and then something else, one of the other twos. So there's like 112 here. Oh, but it's, So what we do depends on what the other values are. Yeah, so like if this is a 12, if this is really big and this is really big, we might want to pick these two. Root it at the biggest node, and then say, I guess some sort of like DP if like parent edge is colored. And then which node you're at. What does this even equal? Equals the min cost. So what are your choices? If you're, oh, maybe this is actually promising. Wait, maybe, does this actually work? So is it just this? Seems unlikely, but if your parent edge is colored, then yeah, so if edge colored, then you need to pick, like, you're satisfied. You're satisfied always. Pick one kid to color, and the rest, oh yeah, and then the rest you would pair up with each other. Yeah, and the rest are uncolored. Okay. Otherwise, okay, yeah. Else, are you max of subtree? If you're not, yes, then like you need to color one kid. What if you're not? Then you don't matter. You'll be satisfied anyway. Seems pretty easy. Okay, let's go over it one more time because we're not getting G. If this round was written well. Can we get, like, what's our estimated rating change here? Okay, yeah, it looks like we're just not getting G. So just, okay. My friends, come on. All right, let's talk about this. So, friends are doing well. Whoa, jeez. Well done, guys. All right, good job. Geothermal had this like a full hour ago. Speedy. Okay, so yeah, the root's a bit tricky. Other than the root, we have a DP for is the parent colored, and then which node we're at. This is the min cost. If the edge is colored, then we pick one kid to color, and everybody else uncolored. Yeah, so it's easy. Otherwise, we just need to know for our subtree max. Okay, then what about the root kid? Then for the root, we pick two kids to color. Yeah, okay. Well, I guess that doesn't matter. Okay. Subtree max, node parent. Yes, we probably do that. All right. Public void DFS. Node from. Okay. So then, what are we printing? The minimum required number of coins. So this max gets, so we assign all the parents, okay, and then subtree max equals value. Okay, so now we have this. Go root. What does this do? We need to color two things. Ah, time flies, man. Okay, so oh man, this has to not be a root either. Oh, okay, so this is why the third case exists. Okay, if n equals 2, so what is this? Then this is if n dot adjacent dot size is less than 2, continue. Max equals null. Or this thing dot adjacent dot size. Or this thing. All right, cool. So we've got this. So this returns non.compare. Cost covered or uncovered? So we want so this will put the bigger one first. Yeah. Okay. And then where's our collections dot sort adjacency? Okay. Oh crap, we need to know what this is. Crap. Dang it. Dang it. Okay. Think. Let's just not pay for it. We can't afford to pay for it, so let's just not. Okay. If you can't pay for something, get your parents to buy it for you. Lesson of the day. Okay, so then otherwise we have at least one kid that we're paying for. Yeah. So for node n in adjacency size, in adjacency, I mean, and dot go pair covered, and then dot go pair not covered. Oh, 0. sort these. Then we have one ants equals 0, and then return ants. And then we've got this stuff. Yeah. So one guy gets covered, the rest are free. Yeah. All right. Oh, wait, we need to, okay. There's one biggest leaf, I think it's valued that. That's not necessarily true. Okay, so we'll think about this later. Handle the case where the biggest value is a leaf. Okay. Time is running out. Time waits for no one. Parent not covered. So if your parent is not covered, what is this? Your parent is not covered, so you have to pay for it yourself. So if you're alone here, then it's just you. Otherwise, if value equals subtree max, then you need to pay for one. Yeah, then you need to pay for one. Okay, so yeah, then long cost equals 0. Okay. Wait, cost plus equals. This is not clean. Okay. So, cost, let's make this ants. Oh, let's do this. Okay, so ants plus equals value, and then here we say it's less than 1, it's covered, otherwise it's uncovered. It's 0, it's covered, otherwise it's uncovered. Okay. Yeah, I think that's fine. I think we're fine. Yes, yes. Oh, and then, so this is return Cost covered equals answer. Turn cost uncovered equals answer. Okay. All right, so that's good. So now we just have this case left. What if, well, let's first, I guess let's just run. No. Straight up wrong. Oh, for this root, you got to pay for the root twice. Yeah, okay. 5, so this should be fine for now. Why is it not fine? Okay, let's debug quick, I guess. Okay, so we have, well, what is the root? So we have 1 to 3, 3 to 4, 3 to 2, 5 to 4. Okay, and the values are $1, $3, $3, $1, $3. Okay. So 3 plus 3 plus 1. Yes. I guess we can do this. Yeah. All right, and then go root. Yeah, that's fine. Okay, so then has a cost of 0, 4 has a cost of 0, or 3 if it's uncovered. Okay. Well, so this is easy, right? It's 3 plus 3 plus. What's wrong with this? Yeah, it's 1 plus 3 plus 3. 3 plus 3 plus 1. Okay, at zero, 6. Yeah. Covering this saves 1, covering this doesn't. Okay, so this sort is broken. So compare 2 is wrong. Compare 2. Covered minus uncovered. O covered, O uncovered. How much do you save? Oh, this is backwards. Okay. So now it's fine. We'll just leave it like that. It's not as clean as it could be. Okay. And this is just going to be 12. What? Man, the test case that I said was stupid is the one that I failed first try. Okay, so we are so close to solving this problem. We just need the case where the biggest value is a leaf. Because we're going to find the wrong maximum then. If the biggest value is a leaf, we find some maximum. Yeah, the maximum we find is not the right one. If the biggest value is a leaf, do we take just this guy? Can be anybody else, but one of the maximums will be this. We don't need the print. Okay, so we get the max leaf's value. Okay, so now if max leaf dot value is greater than max dot value, max equals max leaf dot get okay, so what are we saying here? We're saying if the maximum is a leaf, we're going to go through one of the things adjacent to it. Yeah, because we need to cover 2 things, so whatever. Oh, but we need to just change its value. Yeah. Then one of the kids will be the max leaf. Yeah. Okay. What? what now? What now? What now? Now we remove our debug. Are we gonna need stack trick? That'd be annoying. Don't TLE. Very good. Man, really, is this? I thought I'm doing pretty well here. I don't know. I thought that was pretty good. I thought it was a pretty good contest. What's my predicted rating delta now? Ew, that's cold. Gross. Come on. Cookie. What is it called? Carrot something? CF predictor. The Lost Cookie. Such a sad name. It's a good name though. The Lost Cookie. I guess read G. I'm one problem short of tourist, guys. Like, I can't really complain here. Birthday. Vitaly gave Maxim M as N numbers, 1 to N, for his 16th birthday. Maxim was tired of playing board games during the celebration, so he decided to play with these numbers. In one step, Maxim can choose 2 numbers, X and Y, from the numbers he has. Choose 2 numbers, throw them away. Ooh, these are scary bounds. Choose 2 numbers, throw them away, and add 2 numbers, their sum and their absolute value of their difference. He wants all numbers to be equal after several steps and the sum of numbers to be minimal. Help Maxim find a solution. His friends don't want to wait too long, so the number of steps in the solution would equal or would not exceed 20n. It's guaranteed that under the given constraints, a solution exists. Or if a solution exists, then don't say it's guaranteed. Say it can be proven. Guys, come on, problem writers. Read Second Thread's blogs, please. Yeah, say it can be proven. I think that's what you mean. Guys, contest writers. Okay. Are we gonna, here we go. Where's my, how am I doing? Do I hack people? Are there any hacks going on? Looks like hacks are not the play. There's one hack on what? What was this hack on? Curly? A. Okay. How's my A doing? This is the perfect time to hack, guys. This really is. What was my A? Check if it's sorted. Yeah, if there's ever a decrease, okay, a bigger bounds. How big are the bounds? What are the bounds? 10 to the 4. Okay. All right. Read in V. What? Oh, wait. Okay, so read in the array. Flag equals 1. Set it to -1 maybe. So if this thing is less than or equal to the next one, set this to this. Yeah, okay, that's fine. Excuse me. This is promising. Took him a bunch of tries. Let's see. Copy. I guess that probably works. Yeah, okay. Is sorted. So he's got the right idea. How does is sorted work? Is there a method is sorted? That's funny. Okay. Wait, you had a special case for n less than 2? Come on, Codeforces. Come on, Codeforces. Come on. Come on, you can do it. You can do it. If n is less than 2. Yeah, so, well, that's boring. Whoa. Whoa. Alert. This sounds sketchy. Okay. Prev v. Oh, is he doing the prefix maxes and suffix? Is this like just another way of checking if it's sorted? Probably. Okay, so n things full of zeros. Can these be negative? No. Max of. Okay, so you get the prefix maxes, looks like, and the suffix maxes. Oh, the prefix maxes, suffix mins. Yeah, that's the same. It's just checking if it's sorted. So you're fine. Most people will probably be fine here, I imagine. Sort. Sorted plus n. Oh, yeah, that's fine because of how pointers work. You make a copy of it? You do, yeah. Okay, that's fine. You got an array. Solved equals false. If this thing is less than this, solved equals true break. Yeah, okay, that's right. Whoa, that's clean. Aha, that's very clean. I'm impressed. All right, what's going on here? Some sketchy stuff. Sketchy stuff, main. Okay. What is work? Okay, work. N equals read. We've got some DP. Yeah, you know you're doing something wrong when you're doing it. 2 DPs for problem A. Okay. All right, what's going on here? This is the kind of thing that's likely to be wrong. DP at I equals max of DP at I minus 1. Yeah, prefix max, suffix min thing, yeah. So again, just prefix max, suffix min. Yeah, it looks like, ooh, this is sketchy. This is an off by 1, isn't it? Oh wait, you put, okay, I see. So you put a 0 in the beginning and then infinity at the end. Yeah, so I guess that's fine then. We have n, some stuff. Okay, flag is true, sort the things. We have two things. We've got v and k. I guess that's like the make a copy constructor. Yeah, unlucky. Looks like all these people are pretty right. Sorted v, yeah. Yeah. Okay, time's up. All right, fun contest. I don't think we did too badly. We won our room, right? It's always fun. This guy is going insane. Look how little points he got for solving G. Oof, rough contest, huh? How do we do overall? Can we get our predicted rating change here? 284. I'm not upset about that, but I don't know. How do we do in other global rounds? It's not great, that's for sure. Okay, so yeah, look at this. We went up after getting 1/90th in a div 1. So we probably went up here. That's going down. Goodbye, we got 300th and went up. So yeah, so we got a positive delta here probably. Certainly for master, maybe not, I don't know, not great, but we beat a couple of reds here, I think. Lost to some purples. How'd our friends do? That's the question. Okay, we're on the second page of friends list. That's never a good sign. This guy, what did he do? Oh, he was in Hacker Cup finals. Yeah. Is this FFT? Same as me. A little bit slower, but no right answers, I guess. Is that how he did? I guess. Anybody go ham? Tourist won. Well done. Omnic second place. Kevin in 5th. Good job. All around. Eknerwala, 14th place. Certainly not bad. Anton, 19th. Popping off. Gotta love it. Geothermal, solid 50th. Beating William Lin. Very impressive. I'm sure William Lin isn't too happy with the 50th. But I don't know. I would be very happy with the 50th. I'd be happy with it. RobeZH, I think that's probably going down. All of this is like, I don't actually have people's projected rating changes, so I don't know where they expect to be, but yeah. Decent job here, pretty good. Beat me, it's always a good sign. For you, I guess. Anyway, okay. Yep, not bad. I don't know, we'll see. So I certainly think that's a positive delta for a master. I don't think it's red level. We might need to improve our performance a little bit better, but I don't know. It always feels good to solve A through F, right? All right. Yeah, let's discuss solutions then. What do you say? Solution time. All right, here we go. Problem A. Well, let's just open all of them here. D, E, F. Yeah, A through F. Okay. Sorting pairs. We have an array A of length n, and we can, yeah, okay, so this problem. Okay, so here's the question. So we're going to pick some prefix of an array and some suffix of an array and like split the array in half. And now the question is, will the array be sorted? Or like, is it possible the array won't be sorted after we do this, depending on which position we pick? So like as an example, if we have this last array, since the array is already sorted, there's no place that we can pick that wouldn't have the array be sorted after we do this operation. But in this array here, we can pick this last element here and sort just the 1 and then sort the 1, 2, 3 in the beginning. And then we get 1, 2, 3 and then a 1. So it turns out if there is ever a decrease in the array and we sort the array along that decrease, the decrease will still be there. So let's look at an example. Let's say we've got some numbers here. It doesn't really matter what they are. And then we have a 7. If after the 7 we have a 4, this is like a decrease right here. So when we sort this first half, the 7 might increase, but it's not going to get smaller, which means if there's ever a decrease, it's possible. The only time there isn't a decrease is if the array is already sorted. So basically, this problem is just check whether an array is sorted, and that's it. Cool. Yeah, that's a solution to problem A. I thought it was a very, very clever problem. I really liked it. Yeah. All right, problem B, mex and array. So in this problem, we have some array, and we're going to split it up into chunks. And then within each, sorry, I guess you can see this. This is fine. Okay. Then we're going to split it up into chunks, and then for each chunk, we're going to take the mex, and then we get 1 point per chunk, and we also get 1 point per like mex value, right? So if the mex is 5, we get 5 points plus an extra point for there being, okay, so if the mex is 5, we get 6 points. We get 5 points for the mex of 5, and then 1 point for just the bonus mex for having that group. So then the question is, we want to partition it however we want, and then we want to maximize the sum of like partition scores. And each score is just like 1 plus its mex. Okay, that makes sense. So that's the problem. Except we're not doing that for just the array. We want to do it for all continuous ranges in the array. So the first question is, if we have just one array, how do we do it? Like, how do we split up the array, and then what is the answer going to be? And it turns out that, let's just look at this for a minute here. Let's do the example they give us, because they give this example to try and trick us. If we have the array 2, 0, 1, what we can do is we can split the array like this. So we can cut it here, and then we have a 2. So this has a mex of 0, but we get a +1 for it being a group. And this part has a mex of, it's got a 0, it's got a 1, but it doesn't have a 2. So a 2 + 1. So our final score for this group is, 2 + 1 + 1, so 4 equals 4. Now, what you can notice is that we could have just split it at every position and we get the same thing. So this 1 here, we get a +1 for it because like it's part of a group that has a 0. But instead, we could get a +1 for this 1 by it being the beginning of its own group, right? So sometimes it's beneficial, like it's sometimes beneficial to split things into their own group, but it's never better for something to be part of some other group than it is for it to just be in its own group. So we might as well just chop this array into all these pieces and then evaluate this as it is. And if we know the array is all chopped into pieces, that makes it super easy because we know the mex is always going to be either 0 or 1. The only time the mex is 1 is if the only element in that piece is a 0, because then the mex will be 1. Otherwise, that element is something other than a 0, which means it doesn't have a 0, so the mex is going to be 0. So that's the idea behind problem B. And conveniently, the bounds are small enough that you don't really have to worry about how to implement it. It's just very straightforward. So we can just brute force the L and R and then count how many zeros are in the range. And then, for everything in the range, we'll get 1 point, or if it's a 0, we'll get 2 points. That's just what this is doing here. Okay, that's problem B. Let's talk about problem C. Andrew and stones. Andrew has n piles with stones. The ith pile contains ai stones. He wants to make his table clean, so he puts all of the stones in either the first or the last pile. And he does this by taking 2 stones from a pile, moving 1 to the right and moving 1 to the left. That's what's going on here. So the question is, how do you do it? And the answer is, it's very complicated. You got to be super careful. Yeah, let's talk about all the cases. Okay. So usually it is possible to do. We can get a fresh sheet of paper to talk about why. So I guess as some example, we might have like a 2, 2, 3, and then we'll have a pile in the beginning and a pile in the end, but it doesn't matter how many stones are in there because they'll just get disappeared. So what we can do in general is we're going to start with all of the odd stones because those are a bit harder to handle. And when we have an odd stone, what we'll do is we'll try and make it even. So here we'll take this 3, right? And there are no other odds, so we'll put one of the 3 things here and one of them here. And then after that, we're left with 2, 2, 1. Now we can't decrease the 1 anymore, which means we have to take one of the even elements and move it to the 1. So we'll take this 2, we'll make this a 2, we'll put one thing here, and then we'll throw 1 away. And then we have 0, 2, 2. And then in 2 turns, we can get 0, 0, 2, and 0, 0, 0. So this is the case when you have an odd number. This is what you want to do in general. Now there are some times when you don't have even numbers to fix those odd numbers. So one example is if you have like a 1 and a 3. In this case, what you can do is still solve it by doing like 1, 3 and empty baskets on each side. You can say you give one of the 3's to the 1, and then you're going to give one of the 1's back to the 3. So you'll make both of them even for some period of time. So the 3, you'll get a 2 and then a 1. And then after this 2, we'll give 1 back to the 1. So you'll have 0, 2, and then you can do 0, 0. So this is when you give this back here. So the number of stones that don't get thrown away is just the number of odd numbers in general, most of the time. There are some special cases though, and you got to catch all of them. So one case is like, what if you just have a 3 by itself? Well, it turns out if you have a 3 with like some zeros on each side, this is not possible. And the reason it's not is because you don't have anything to give the 3 something back. The 3 will get stuck at a 1, and you can't fix it. So like this is impossible. The other case that's impossible is if you have like, but like, okay, to be clear, 5 is possible though. So if you have 5 with like a 0 here, you can give a 1 here, so you can do 1, 3, and now you have a 1. So now you can do 1, or you can do, yeah, you can do 1, 2, and now you can give 1 back here. So you can do 2, 0, and then 0, 0. And that's the idea if you have a 5 or a bigger odd number. In this case though, it takes one more turn than you would predict. So you're going to take, like normally you would take 1 turn because the 5's odd, but you also create another odd number. So you have that turn as well. So you've got the 1 turn to give a number here, and you kind of do that a second time, but you don't pay for it because you remove both of them at once. And then you also give a number back to the 5. So you have to add another one for that. So in total, 5 takes 2 turns to get rid of the evens, and then 2 additional turns for the 2 that get passed back and forth. So that's that case, which is possible. But if it's a 3, it's not possible. However, if it is a 5, it still might not be possible if you don't have any room. So if you have just a 5, but those 2 are on the ends, you can't ever take from the ends and put it back in the middle. So if you have a 5 with no room, or a 5 or bigger, like a 7 and an 11 with no room, it's going to be impossible then as well. Anything else? I think that's all the cases. I guess the only other case is if it's empty, then it's possible. So let's look at the code here. See if I hit all of them. Okay. So what I do is I go through the entire array. I count how many non-zero elements in the middle there are, what the max of all of these are to see if it's a 3 or a 5 case, how many 1s are in the middle, and how many odd things are in the middle. And this just counts all of them. So the logic there is pretty boring. n pairs is like the number of times I'll take a 2 and remove it, assuming everything else works, assuming all the odds work out. So yeah, that's just going to be like the base for my answer at the end. So first of all, if everything is a 0, the answer is 0. Also, if everything is a 1, I guess I didn't mention this, but if everything's a 1, the answer is -1 because there's no way to delete any of those 1s, so you're just stuck. Okay, these are the other cases. So if you have just a 3, and that's the only thing you have that's non-zero, it's impossible. Otherwise, if you have just like a 5 or whatever, but no room to fix it, then it's impossible. Otherwise, if you have the 5 thing, but everything else is even, then, wait, is this right? Just a 5 case. Oh yeah, if, yeah. So if you don't have any 2s, not everything else is even. If everything else is 0, then you don't have any 2s to give a 1 to the 5. So the 5 has to give a 1 back to itself, which means it creates another odd number doing that. So yeah, that's this case. So my code is right. My logic was a little wrong when I discussed it just now. And then finally, like I mentioned, it's the number of odds that you're shuffling back and forth plus the number of pairs. That's the answer. Okay, that's the solution to problem C. Very good, very good. Let's talk about problem D, yet another minimization problem. Okay, we have 2 arrays, A and B, both of length n. And what you can do is if you write the arrays one on top of the other, you can flip a pair of elements that's in the same position. So you can flip like the third element of A with the third element of B, you can just swap them. And you do this as many times as you want, so you can like do some flips. And at the end, what you're gonna do is look at all pairs of elements in one array and all pairs of elements in the other array, and get the sum of this pair and then square that. And you want the sum over all of those pairs. And you want to minimize that total cost. If you wanted to maximize it, it would be a really easy problem. You just put all the bigger numbers in one array, smaller numbers in the other array. But this is a bit harder. So the question is, how do you minimize it? Conveniently, n is very small. N's small, and also the bounds of numbers are small. So we can like maybe do a dp. And that's kind of one idea we're gonna immediately gravitate towards. Since I know the solution, kind of spoiling it a bit. But let's talk about it on paper. Okay, so first thing, we're gonna do some math. It's pretty basic math, but still helpful to know. If we have 2 numbers, x and y, the cost they'll contribute is x plus y squared. If we FOIL this, you get x squared plus 2xy plus y squared. So what this means is that we can kind of ignore this part and this part, right? Because this x squared and y squared, we're gonna be paying for these things regardless of which swaps we do. Every element will be in n-1 pairs in its half. So we're always gonna pay this x squared cost for every element, and we're gonna pay it n-1 times. And same thing for the y's. So really, the only thing we actually have, like we can calculate this in the beginning and just ignore it. The only thing we actually are trying to minimize is this 2xy part. So instead of worrying about this, let's worry about minimizing this 2xy. Now we're gonna have a factor of 2 always, so we can ignore that. So really we wanna minimize xy. So in other words, we want to swap these elements in such a way not to minimize what they told us to, but to minimize the product of all pairs summed up. Okay, so if we want the product of all pairs summed up, the question is, what does one thing contribute, right? What does, if we have some elements here, right? Let's say this is a 3. We got some more elements here. What does this 3 contribute to the cost? Now we're gonna be doing all pairs, so it's like half of everything that it's in. But an easier way of thinking about it, in my opinion, is we'll associate the cost to whichever one is farther to the right. So the 3 will contribute a cost of 3 times whatever this sum is, the sum of these 3 elements. And that's what 3 will be responsible for. And then the stuff to the right of 3 will be responsible for all of the pairs that include the 3 as well. So the stuff to the right of 3 will be responsible for itself and the 3. And the 3 is responsible for itself and the stuff to its left. Okay, so it's this sum that we're interested in. So when we have these two values here, we have a 3 and then we have another value. Maybe this is like a 5, right? What we're interested in is a couple things. We need to know what is the sum of this part? What is the sum of this part? If we're looking at just this part of the array, we need to know this sum and this sum. And we also need to know that we're on this index. And from that, we can figure out whether we should have it this way or whether we should flip them. That's the idea. So we need to know these two sums, and we need this. And based on that information, we can make our decision. So that's the DP state. The DP state is like the sum, DP at like the prefix sum, prefix top. We also need to know the prefix bottom. And then the index. And then the cost we pay here is either 3 times this plus 5 times this, or 5 times this plus 3 times this. And then the top and bottom sums will adjust accordingly for the future values for what looks at us. Now, you might be saying, David, the prefix top sum can be huge. This number can be 10 to the 4. This can also be 10 to the 4, and this can be 100. So right now you're looking at a runtime of about 10 to the 10. That's not going to run in 2 seconds unless you write really fast C++ code. And you would be right. So what we can notice is that these 3 values aren't all independent. In particular, if you know the prefix top sum and you know the index, you know the prefix bottom sum, right? So you don't actually need to store this in your state because it is redundant. Right? If you have the top, the sum of the elements in the top, you know what the sum of the elements in the top and the bottom are. So the prefix bottom is just like the prefix sum of this many elements minus the prefix sum at the top. And that's what you're going for. So yeah, that's the idea for how you can make your state small. And your transition is ordered 2. I did it slightly differently, but I'll talk about my solution real quick here. Yeah, so here's how my solution works. You've got the 2 arrays, and my DP stores the top minus the bottom, which is a bit more annoying, but still works. You just have to like be careful that you never pass any offsets. You got to be a little annoying about it, and you got to do some math, some addition, subtraction that you otherwise wouldn't need to. But basically, this DP stores for some top minus bottom value. If the prefix sum on the top is this much more than the prefix sum on the bottom, and this is the position you're at, what is the minimum pairwise product? Yeah, so sometimes it's impossible, and it might be impossible if this offset is too big, or it might be impossible if the parity doesn't line up with the parity of the array. So that happens here. No, that happens here. And it might be impossible if it's just not possible to like shuffle the numbers to get that parity early enough. And in that case, I just return a really big number, so it's not the best answer. But yeah, that's basically how this DP works. I won't cover all the details because it's kind of a lot of code. But it's, yeah, you can, I guess, pause it and look through it. Here, let's... Yeah, so yeah, you can see the whole DP here. Not too exciting. Most of I think this all is just copy pasted from the thing above, so you could write this cleaner if you wanted. But that's the DP part. The actual answer is just we're gonna brute force what the prefix sum at the end is, and we know it's gonna be one of like 20,000 things. So we'll look through all 20,000, see which one of them is best. And then we also know every element in both arrays it's like value squared contributes n minus 1 times. So we can add that to the answer as well. And that's problem E. Okay, problem D, I mean. Problem E comes next. Wait, that was problem E. Nope, that was problem E. Problem E is separate. Best pair. Okay. How does this one work? We've got some array, and we want to maximize this value. So we're going to pick two values, x and y. And the score of these two values is equal to the sum of the values times the sum of the frequencies of those two values. So if we pick 7 and 10, it'll be 17, which is 7 plus 10, times the number of positions in the array, which are either a 7 or a 10. Okay, I think that description makes more sense than this. So 17, because 7 plus 10 is 17, times the number of positions in the array that are either a 7 or a 10. Okay, but the way they wrote it is kind of helpful here because it separates out counts of 7 and counts of 10. In particular, for solution ideas, I guess the bounds are kind of important. So each of the elements can be really big, but we have like 3 times 10 to the 5th elements. Also, there's this additional constraint here, which is the number of, there are some bad pairs. So we want to know like the best pair of x and y we can pick that does this, but they're like also ignore these things, right? So yeah, ignore some xy pairs is basically what they're saying here. So like, what's the best one that isn't in this set we give you? And then you have to tell them that. Okay, so how do you do this? First main observation here. In an array of 300,000 elements, the most number of distinct counts you can have is about square root of 300,000, right? If you have, because your first thing can appear once, the next thing will appear twice, the next thing will appear 3 times. And like 1 plus 2 plus 3 plus 4 plus 5, that gets to be, it grows at an n squared rate. So those numbers start getting big faster than order n. In fact, they start getting big around n squared because the sum of those numbers is like n squared over 2. So you get like 2 times square root n elements, which means what we're going to try to solve this problem is we're going to try brute forcing all count x and count y pairs, right? So if they didn't give us this bad pair restriction, what we could do is say, how many times is x going to appear? How many times is y going to appear? And given we know each of these things, we just want the biggest thing that appears x times and the biggest thing that appears y times. And we can try this over all like n squared pairs of frequencies, but in reality, like there are only square root n frequencies that matter. So we only have order n pairs of frequencies because square root n squared is just order n. So we're going to try all pairs of frequencies. That's what I'm getting at here. Then within each frequency, we have like a whole bunch of types of elements, or a whole bunch of values where each value appears this number of times. So we need to see, like, if we've got these 2 buckets, we need to figure out what's the best way of picking one thing from one bucket and one thing from the other bucket. That's the maximum sum, assuming we can't pick an illegal pair. So let's draw this out so you guys know what I'm talking about here. All right, so we've got some array, and we decided that one of these things is going to occur 6 times, and the elements that occur 6 times are like 1 occurs 6 times, 3 occurs 6 times, 7 occurs 6 times, and 10 occurs 6 times. And the other element, one's going to occur 6 times, the other element's going to occur 4 times. And the ones that occur 4 times are 8. There are 4 8s in the array, and there are 4 2s in the array. Okay, so, and maybe that's it. Okay. And then there are also some bad pairs. So it's possible 8 and 10 are a bad pair. Maybe 8 and 7 are a bad pair. 8 and 3 are a bad pair, and 2 and 7 are a bad pair. So we want to know of all of these pairs that aren't bad. So 2 and 10 is 1, 2 and 3, 2 and 1, 8 and 1. Which one is the best? Okay. Key observation about how these pairs are structured. We also have like, this is like a times 6. These occur 6 times and these occur 8 times, I guess is what we decided. But key observation is that if you have some pair, like 7, 8, you know 7, 8 is going to be strictly better than 7, 2. Right? It's always better to pick the 7 and the 8 than the 7 and the 2. The only reason you wouldn't pick the 8 and the 10 is if it's a bad pair, which in this case it is. But what this means is we can skip a lot of our computation, right? So we can make sure the only things we check that waste our time are things that were in the input. And there can't be that many things in the input. There can only be 300,000 bad pairs. So if we only waste our time looking at those, our runtime will be pretty quick. And here's how we do this. If we're given these two arrays, what we're going to do is we're going to like brute force. We're going to go like this, and we're going to brute force which bottom element we pick. So we'll start with this 8 here, and then we'll try 8 and 10, 8 and 7, 8 and 3, 8 and 1, until we find something that works. Once we find this 8 and 1, we know no other element, no other thing on the bottom will use any of these, so we can cross all of these out. Also, if we get to this 1, that means that we've used up 3 of these edges, so we'll never see these edges again, right? So we can remove like 3 from our maximum total amount of runtime. And that means each time we check a pair, we remove something from our runtime. We can only do that 300,000 times. So our runtime is going to be order n plus m when we're done. Okay, so we did that for the 8. Now let's move on to the 2. So the 2 will try the 10, and this works, right? So 2 and 10 is legit. And we compare 2 and 10 and 1 and 8. And if we're ever smaller than the 1 and 8, we can break out. But also, in this case, the 2 and 10 is going to be bigger than 2 and 7, 2 and 3, 2 and 1. So we can break out early here too, and we can get rid of all of these things. In fact, we can also get rid of the 10, because anything smaller than 2, right? If we had like let's say we had 0 here. Just imagine, I mean, obviously 0 won't be the best, but let's just imagine it was. Maybe, actually it could be the best, but zeros aren't allowed in the array. But if you ignore this for a moment, we know something smaller than this 2 will never be better, like this and 10 will never be better than 2 and 10. So since 2 and 10 was allowed, we can just break out instantly. We can stop looking at, not only can we stop looking at all these elements, but we can stop looking at all of these elements as well. So by doing that, the total number of checks that we'll do will be the number of unique frequencies squared, that's just n, plus the number of times that it's wrong. And that will be, the number of times we get it wrong is just m, like the number of bad pairs. And that's the idea. Okay, so I thought it was a very cool problem. Maybe like not super unique, but look at my giant pile of papers here. Look at all this paper. The Lorax would kill me. Let's look at the code. Oh, I've done something. Okay. I've turned on breadcrumbs. Can we turn off breadcrumbs here? Thank you. Okay, so yeah, this is a bit messy, to be honest, or just a bit long. But first of all, I coordinate compress things to make it easier, or maybe a bit faster, and then I store a list of all of these bad pairs as longs. In C++, obviously you just do pairs, but Java doesn't have pairs, so you put both the ints inside of a long. And then we have this value of ID. This is the value, like when I coordinate compress, I need to like map this thing back to its value, so that's what this is doing. Coordinate compression happens here. It's pretty straightforward. I've done it a million times. Feel free to pause and take a look. But basically this like converts, it gets rid of all the empty space in the numbers so that I can use arrays instead of hash maps everywhere. Okay, so that's what's happening there. What else is going on here? We read in all the bad pairs into a hash set, and I have this toLong method which just puts them into a long. And then later on I can check whether something is bad for coordinate compressed A and B's. Okay, so that's what's going on in the input. Next, I build the buckets. So first of all, I count how many times each element appears. That's what this thing's doing. And then I put these IDs inside buckets. So a bucket will have, like bucket 3 has all of the compressed elements that occur 3 times. And that's what this is doing. Finally, I look at all pairs of buckets, and I get the max using the method we just talked about, which will be fast when it's amortized, but it could be like order m per thing, but in total it's also going to be order m, so it's fine. We get the max here, and take the best answer among all of them. Okay, so last part of this description is what does this get max do? And here's what it does. We have these two arrays, and we also have the counts of how many times each thing appears for evaluating how good something is. Okay, so basically, I take the smaller array. This is not necessary, but I do it anyway. Yeah, you can ignore this. So for the bottom array, I'm going to iterate through it from right to left. That's what's happening here. Yeah, this part's, you don't need to put the smaller one on the bottom, but I did anyway, because I was paranoid, I guess. Oh well. I'm a human. I make mistakes. Yeah, so the bottom one I'm going from right to left on. And then this is the top one on the top, which I'm also going from right to left. And for this thing, for the guy on the top, I keep going until I hit something that's already been matched with a better guy in the bottom. So initially nobody has, so I want to check all the ones on the top. But eventually, if I match with someone on the top, I don't want to match with him or anyone.
Error 5.
Roomba. Sorry. My Roomba's being obnoxious. If I have a guy on the bottom which matches with someone on the top, I don't want to match with him or anyone worse than him for anyone worse than the guy on the bottom, because it'll just be a worse pair. So that's what's happening here. Okay. All right. So then I evaluate this. If it's worse than best, even if it's not legal, if it's worse than best, I'll break out. Because I want to break out as quickly as possible. Make sure this is very, very much not n squared. Okay, otherwise, if this thing isn't bad, that means it's going to be the new best. So I set this best on the big half, and I break out. And also, if this is the first thing that I match with on the top, then I don't want to be doing this loop n times, because this loop could be really big, right? So if this is the best one possible, and I know all future versions of this loop will break, then I have to skip this part. This is like a very useful thing to do. So that's the idea. Yeah, that's the idea for problem E. And then evaluation is kind of boring. Okay, cool. Yeah, that's problem E. Good. Last one, problem F, towers. Okay, so in this problem, we have a tree. We're given a tree. And we're going to build some towers, some like cell signal towers. And we need to give everybody cell service. So somebody has cell service. If there are two other towers somewhere on the tree where the path between them contains us, like we have cell service, if the path contains us, and both of those towers are at least as tall as our building, as our height. So yes, that's the idea. Now the question is, what's the minimum sum of heights that you need to build towers for so that everybody has cell service given the heights of all of the nodes on the tree? Let's do an example. Let's do the second example because it's a good example. We're running low on paper here, but we got one problem left, so we'll try and make it work. Okay, in example 2, you've got some nodes. You've got this 1 node, you've got a 3 node, you've got a 4 node and a 5 node, and then you have a 2 node. So this is what the tree looks like. Additionally, every node has some costs. So node 1 costs $1. Node 2 costs $3. It has a height of 3. Node 3 has a height of 3. Node 4 has a height of 1. And node 5 has a height of 3. So what the answer is we're going to build one tower here. Leaning Tower of Pizza, maybe? I don't know. Pizza? I think it looks like that. We'll build a tower here. We'll build a tower here. And we'll build the tower here. And the heights are going to be, this will be 3 tall, this will be 3 tall, and this will be 1 tall. Is everything satisfied? So let's look. This one is satisfied because it's height 1, and you have this path from the 3 to the 1, where both are at least as tall as this one. We also have the path from the 3 to the 3, so this could be up to height 3. It'd still work. This one is satisfied because there are 2 different things. There's this one, and there's this other 3. Both of them are sufficiently tall. You can't pick this 3 and also this 3, which is kind of silly, but that's just how the problem is. So you pick these 2 elements, and this path includes this. These 2 are different, and also these 2 are at least height 3. This one here also works because we have the 3 and the 3 that pass it. This one works because we have the 3 and the 1 right here and here. And both of those are at least height 1, and they include this node in the path. So that's the sample. Okay, so what you notice from this is that, well, we only picked leaves. Maybe that's true always, and clearly it is, right? So you would never want to build a tower here. If we're going to build a tower here, maybe it's like to help this node or something, maybe it's to help some other node, we might as well move it to the leaf, whichever leaf we want. And we can combine the, so like if we build a tower here of height, I don't know, I don't even know what we do, but whatever height, we can just move it and combine it with a leaf tower, right? There's always a leaf tower we can combine it with. I won't prove that formally, but it's always just beneficial. So we would never want to build something there. So we're only going to build towers at leaves. I guess the more formal reason for this is that, like, if you build a tower at some position, it's not going to be used in all directions. Because if it's used in all directions, then the tower is completely unnecessary. Because, like, it's going to be the smaller of those 2. If it's the bigger of those 2, you could decrease its value. So it's going to be the smaller of those 2, which means if it's used in all directions, that means, like, if it's used going left and used going right, you can just remove it and then use the 2 towers on either side. And those are perfectly good. So yeah, there's no reason to have a tower that's like smaller on both sides. So if this tower is bigger on both sides, that means there's one side, one of many sides, that is not used for. Just push it into that leaf, right? Just put the tower on that leaf, and now you don't have to pay as much on the leaf because you're paying, like, the cost in leaf was unnecessary before. Obviously, you also need to put a tower on every leaf. You can't have any leaves without a tower, because the only paths that include leaves are paths where that leaf is an endpoint. So we're going to put a tower 1 on every leaf. Okay, how do we decide what to do what to do? It's not quite as easy as you may think, and I'll give you an example of why not. Let's look at this case. Yeah, so maybe you got like something like this here. Okay, so let's suppose this middle node here is like a really big node, right? It's going to be really big. It's going to need 2 towers put on 2 leaves. First of all, we'll fill in all of the leaves with their current value because we know that they have to at least be that. So maybe this is a 2, this is a 4, this is a 2, and this is a 1. So we got some leaves, and then this thing is like a 12, right? So it's possible that we want to put one of the 12 endpoints here. We'll upgrade the 4 to a 12. That's totally reasonable. However, we can't immediately decide where we want this other thing to go, right? We don't know, like maybe we want to put it at this 2, but maybe we want to put it at this 1 because maybe later on this is going to be a problem. Maybe this is like a 12, but maybe this one's going to be like an 8 or something. And we're going to have to pay for one of these things here. We would really rather not. And we don't have to if we make one of these 12. And then we have to pay a little bit more for this 2, or we have to pay a little bit more to upgrade the 1 to a 12 than we would the 2 to the 12, but we save overall by not having to upgrade the 8, or upgrade either of these to an 8. So yeah, so like this depends what the other nodes are, and some other complicated stuff can go on. So it's gonna be hard to just like decide right away. Probably not possible. So we need to come up with a better way. And clearly, the better way is to do a DP. Dynamic programming. So here's the idea. For each node, there are kind of only two things we care about. You can argue there are more, but I'll explain why there aren't. You kind of only care about whether or not, I guess this is the only thing you care about. You care about what the root is, but we'll root the tree in just a minute. But given that we have some root, you only really care about whether there's going to be some node that's coming down from your parent through you. And if so, you get to decide how to allocate it. But your parent says okay, you need to handle, one of your kids, put a path down to them, upgrade it to what I tell you to, and then that will handle me, make sure I'm safe. You decide how to do it within your kids, but it's got to be somewhere in your subtree. From doing that, we can handle the 12, right? We can say okay, this path needs to handle one of these, and this path needs to handle one of these. We don't necessarily know how to distribute these immediately, but for every node, we can ask, what happens if I told you you need to handle this? And what happens if I told you you don't need to, right? What happens if I told you you need to find a place to put this path? What happens if I told you you're on your own? There are going to be no paths going into this, right? Those are all for yourself. Although you can promise, we will promise there are some other big nodes out there. They just don't cover you, right? You'll have one of the endpoints, just not the other. So that's, I kind of spoiled the idea here, but that's the idea. We're going to first find the biggest node. If it's in the middle, that's easy to handle. Otherwise, we'll worry about that in a minute. But this is the biggest node. And for this, we need to find two of its kids to give these size 12 things to. And we're going to pay for them right now, because otherwise we would have to, this DP gets a bit complicated. We not only have to say whether you have something to upgrade, we'd also have to say what you have to upgrade it to. And that gets hard because then there could be a bunch of things you might upgrade it to, so the DP gets big. So we're going to pay for it here, and then we'll say you now have a free path. We'll pay for it. We'll give you it's not really a blank check. It's a check with a fixed amount of $12. And you can spend this on exactly one node, but that node now no longer has to pay for its own tower, because we need the tower to satisfy this root node here. So we'll root the node here. We're going to do a DP for every node. It has to calculate the cost if it pays for it and if it doesn't. And yeah, you can do that pretty easily. So the one case that's interesting is, let's look at this node here. This node, it might have to be covered. If so, so if a node is going to be covered, you're going to give the path to whichever of its kids benefits from being covered the most. And you can do that just by looking at the two DP values. You know what you have to pay if you don't cover a kid, and if you do, you can just sort the kids by how beneficial is it to cover the kid, so the difference in those two values, and that will tell you the kid you should cover. So you know how you'd spend your covering cost, and then you know the total cost otherwise. If you don't cover, if you're not given this freebie from your parent, then that means you're going to have to pick at least one of your kids to cover you, right? So one of the leaves in your subtree needs to be covered. But if you aren't the max in your subtree, if there's a bigger node than you in your subtree, you know that node will somehow figure it out. It might be a leaf, it might be not a leaf. Whatever that node is, if it's the max, or if it's bigger than you, then it'll cover you because it'll get handled somehow. And there's someone bigger than you outside of your subtree, right? We made one of these nodes a 12. So if this node here isn't the max, and this is an 8, and this is a 6, then this 8 will somehow get handled. So we have an 8 here, we have a 12 here. You can connect the path, it'll cover us. We don't need to worry about us. What if this is the max? So let's say this is a 6, and this is a 1, and this is a 2, like we had earlier. Then, since we're giving we're giving the parents' money to these people, we know there are going to be 2 of these that are a 12. So 2 of them are 12s, and we have our 6 here. that means we want to make one of these things a 6. We don't need to make both of them a 6, because if we make this a 6, this is going to be the best answer, then we can connect this to whatever down here is a 12 that's bigger than us. And that's the idea. So those are the cases. Let's look at what this looks like. Okay, read in the nodes, read in the edges. Then we're going to find the biggest thing. I guess I didn't talk about what to do when it's a leaf, but you just have to pick a node adjacent to a leaf to be the root, and then everything works out. If a leaf is the biggest. So we're going to DFS from whatever we declare to be the root. We do that here. Yep, just do the DFS and get your subtree max. Okay, so there you go. So now we have a rooted tree. And then we have these 3 methods. So we have go root, we have go if your parent covers you, and then we have go if your parent does not cover you. Okay, so yeah, what if you're the root? Well, if you're the root, you're going to first calculate the answers for all your kids, and then you're going to sort them by the ones in the beginning will be the ones that are most beneficial to cover. So that's what's happening here. And now, since you're the root, you got to pick 2 leaves. So you're going to pick the 2 leaves that are best for you, and those ones get covered, the rest of them don't. That's what's happening here. Okay, so now we just have these 2 methods. So what is going to be the cost for this subtree if the parent covers you? Well, if we've already calculated it, return. If we are a child, we're going to let our parents pay for us, and then we don't have to pay anything because we're going to use our parents' voucher, right? Our parents' check. We don't know what this check is for, but we do know our parents are bigger than us, right? All the parents that care are bigger than us. So it will cover whatever we need to pay. It'll cover us. Yeah, and that's because we do the subtree max stuff later on. That's why this always works. Okay, next we look at, so we're covered, which means if we have at least one kid, we want to pick the kids that benefit most from being covered, and those are the ones that we'll hand the voucher to. So that's what's going on here. Yep, we give it to whichever kid is first in line for being sorted for like how much do you need this voucher. Okay, that's the idea. Yep, and then what if the parent isn't covered? So this is the case we just talked about. If you're a leaf and you're not covered, then you just have to build your own tower. Oh well, sometimes you got to do the work yourself. So that's what's happening here. Otherwise, you calculate the answers for all your kids, sort them by which ones benefit most from being covered. And now you know when the root was handled, it picked the 2 biggest nodes. So everything else is going to be smaller than that. So we only need to pick 1 node. We're going to pick 1 node in our subtree. That's what we're going to be covered. But we only want to do that if we're not already covered by our kids. So if we're covered by your kids, then just let your kids handle it. You don't need to worry about yourself. Otherwise, you're going to need to pay for a kid, and you're also going to need to create a voucher. So creating the voucher is when we pay for, here's where we pay for the voucher. And then we need to give our voucher to whichever kid needs it the most. So that's what's happening here. And that's the idea. Okay, this is a little bit messy, but it just sorts by whichever one needs the voucher the most, basically. All right, that's the idea. That's the idea. Okay. How's system testing going? Looks like we passed everything. Did everybody? Are we really 250th place? Kind of brutal, isn't it? Did people fail? Must still be going. Okay, still going. Now we're 251. So it's happening. Okay. Or maybe not. I thought we were like 280 or something, 290. I don't see any failures though. Okay, so system test is still happening, I guess. Yeah, it's still happening, okay. Even though it says it's at 100%. Interesting. Databases are kind of weird, aren't they? Okay. Yep. So I don't know. We'll see. See when we see. I enjoyed the contest. I thought it was good. Other than to the problem writers, stop guaranteeing things. It's annoying. Just don't. Just like say like what was for F? Was it for F? Okay, guaranteed it forms a tree. I guess that's fine. That's not really. Yeah. Okay. Here. Stop. Don't guarantee this. This is no. Like I wrote a whole blog post on this, and it's very annoying. It's my biggest pet peeve. Like I have no doubt what they mean to say here is that like just purely because I've done like 100 contests, I know what they mean here is that if a solution exists, we can prove it. Like there also exists a solution with less than 20 end moves. That's what I'm sure they mean. But like there is no way of reading this that doesn't know that. Like, okay, I'm just ranting at this point. Nobody cares. They use the word guarantee in this problem to mean something is provably true. In an earlier problem, they mean this thing would not be true if we didn't guarantee it. But those two things, like there's no way of distinguishing them because we didn't just pick one of those meanings, right? Here, like you just have to assume you have to assume something about the problem that isn't said, or something about the input constraints that isn't said. Or in the other one, you have to assume something that like I don't know, maybe is true, maybe it's not. And the other one, it was more clear that it wasn't true. And in this one, just because I've done a whole bunch of problems, this is almost certainly true. But it's like it's not clear. You can't say guarantee like this because then when you guarantee something's a tree, people think all graphs are trees, which obviously isn't the case. But like, just say we can prove. We can prove, not it's guaranteed. And the other one says input constraint : this thing. That way you know that it's a constraint on the input and it's not a thing you're proving. Okay, there's my rant. Thank you for coming to my TED Talk. Hope you enjoyed the contest. Have a great day.